the double integral that represents volume of this object. What would that look like generically? Well, okay, V. Okay, it's a double integral. This is something we know how to do. So V, all right, the integrand, if we go with the order dy dx, let's say, that might not be enough room. Hold on. If we go with the order dy dx, then what's the integrand going to look like? Well, you need height values for the integrand, right? And you need a floor and you need a roof. And you can actually use just a vertical line from the bottom function z1 to the top function z2 to give you an idea. It's kind of like a vertical rectangle that you use in the xy plane. So the roof is given up here by z2. The floor is given down here by z1. No matter where you draw that vertical line, this is a nice enough region so that no matter where you draw that vertical line, you're going to have the same roof and the same floor. So if we wanted to get that distance, what would we do with the functions? So the distance, the length of the green line at any particular xy value, what would we do? Subtract. We would take g2 minus g1. And that would be our integrand, wouldn't it? Now you guys are used to the floor being the xy plane, but now we're under the assumption that the floor is something other than the xy plane. Okay? So yeah, you'd have to subtract to get it. g2 xy minus g1 xy. Everybody see why that would be the integrand? I'll explain further in a second. Well, no, I can do it right now. This guy, so dy dx is your area element, right? And then if you multiply by height, which is g2 minus g1, you get volume. When you do actually have a volume, you do get a volume element, don't you? Okay? So that gives you, that g2 minus g1 gives you the height. Height times area gives you volume. Okay? So what would the limits of integration look like? Well, generically speaking, if in the xy plane, then, so if we could think in terms of the xy plane, this would be the region in the xy plane, isn't it? The projection of that object down in the xy plane would be the region that we're integrating over. So if I flip this around, made the y-axis here, I can still do it in black, I guess. And the x-axis here, then I don't know if I can reproduce that region, but I'm trying to flip it in my mind and, you know, turn this little indentation and trying to get something here. But you get the idea, right? Well, this isn't quite a function, is it? So you'd have to split it up into two and hopefully have a top function given by maybe h2 of x, the way we're going to think of it in terms of vertical rectangles. So hopefully we'd have a vertical representative rectangle. So hopefully we'd have an h2 of x and an h1 of x. Two functions of x, y as functions of x. Then the inner limits of integration would be what to what?
h1 x, h2.
h1 to h2. So h1x, h1 of x to h2 of x. This is if we're going with the differential or dy dx. We could always flip the rectangle on its side and change it to dx dy, and then you'd have x in terms of y that way. Hopefully you can do that, right? If you have a nice enough region, a type 1 region or type 2 region. And then the outer limits of integration, well, hopefully you could figure out what the left-hand most x value is here, call it A, and what the right-hand most x value is, call it B. And so the lower limit's A, the upper limit's B. And so you guys have been, you know, dealing with this sort of setup in 15.3 and struggling through it. It's always a struggle to get used to this stuff. Eventually, like anything else, it gets easier, but it's always a struggle. But that's basically generically what you've been doing, right? Generically speaking, So would it be easy enough to change this to a triple integral? Yeah, the integrand then, the functions from the integrand become your limits of integration on the innermost integral if it's a triple integral. So that's what we're going to do. So I'll have to fit it in here so we can see how it relates to the volume integral. So if you switch, or convert maybe would be a better word, convert to a triple integral, then, okay, all you need 3 integrals. And now the innermost integral, the upper and lower limits, the lower limit will be given by the g1, the upper limit by g2. So g1 of xy on the lower limit, g2 of xy on the upper limit. And then we're going to have 3 differentials, dz, dy, dx, when we go in this order anyway. There are going to be 5 other orders that you could set up this integral in, maybe, if you could possibly evaluate it. And then the other ones don't change. h1 of x to h2 of x, and then a to b. And this is, again, this is one possible order. And since the integrand now is 1, we could say that a triple integral with integrand 1 represents volume. So it's like we're integrating over this solid in space. So instead of integrating over a region, an area region, we're integrating now over a solid. Now, do you guys see why the double integral can become this? Because if you would just evaluate the inner integral, maybe I should point at it. If you just evaluate the inner integral with respect to z, you get z evaluated from g1 to g2, which is exactly the integrand in the 2 integral setup, the double integral setup. Okay? So you understand it then. Okay. Well, you know, we're not always going to have an integrand of 1. We're going to stick things in here. What could it possibly represent, though? It's not going to represent a volume anymore if the integrand is anything other than 1. Well, couldn't we stick in a density function where density is given in mass per unit volume? So it's not a planar lamina anymore, it's a solid. And your density function, rho of x, y, z, would give you your density of your solid at any particular point inside the solid. So that's just one application. There are definitely applications of this. We're not just doing it for fun. Okay. So what? Well, we could say in general then, the triple integral over a region Q, let's say. So we could think of this picture as calling it Q, right? It's comprised of 2 functions the way I've drawn it, but we could call it Q. The triple integral over a region Q is given by, okay, here's the notation first of all. We could use the triple integral signs, then underneath that put Q. And then we stick a function in there, f of x, y, z. Stick a function in there. And then we use a dv. So what does dv stand for? dv would be a volume element. Okay? So here's what I want you to think of, and I'm not going to try to draw this because it's too hard for me to draw. Remember, for the double integral, we broke up the region R into a bunch of sub-boxes, right? A grid of sub-boxes. Now think of dividing, and they were 2-dimensional boxes, right? Now think of dividing up Q, this solid region, into a grid, a 3-dimensional grid of 3-dimensional boxes, little sub-boxes that build up and approximate the volume of this region, right? Then dV would be a volume element of one of those boxes if it were infinitesimally small, okay? So dV is considered a volume element of Q. Volume of I'll just say, I don't like spelling infinitesimally, so I'll say a really small sub-box in Q, in the solid Q. And in parentheses, I'll say volume element. And then if you want, now this is just notation, right? In order to actually evaluate the thing, you have to come up with what we would call the iterated integral. And so, in other words, limits of integration. So the f of x, y, z, whatever that is, and then you have to decide on an order of integration, which is indicated by the differentials. The standard order would be dz, dy, dx. But that depends on easily representing the solid, the boundaries, the outer surface of the solid, as functions of z, upper and lower functions of z. If we can't, then we might try some other order of integration. But then, so I'm going to list this one possible order of integration, just rehashing what we just wrote up here as far as the limits go. So inner limit would be z1 to z2 in the form of g1 of xy, g2 of xy. Then when you go with dz, dy, dx, the middle limits of integration will be functions of x. Y equals some functions of x, h1 and h2. And then the end ones will be what x ranges from when you project the solid down into the xy plane. Of course, if you change the dy dx to dx dy, then the middle limits of integration will be x in terms of y, functions of y. And the outer limits will be what y ranges from, the constants that y range from when you project the region into the xy plane. So this is just one of 5 possible setups. Example, find the volume between the paraboloids. Given by z equals x squared plus y squared, and z equals 4 minus x squared minus y squared. And we're going to, not that you'd have to, but for the sake of demonstration, we're going to use a triple integral. Using a triple integral. Now you could use a double integral just as easily, but of course we're not in that section. We're in the section on triple integrals. All right, so what do these things look like? What do these paraboloids look like? They look like, one looks like a bowl going up, and the other looks like a bowl going down. In fact, this other one you can think of as z equals 4 minus the quantity x squared plus y squared. So you can think of z equals the quantity x squared plus y squared being turned upside down by this negative and translated up 4. Okay? And in fact, this is something you should be able to draw, at least a rudimentary drawing. So you guys know what this looks like, right? This z equals x squared plus y squared, the quick way to draw it, something like that, right? And then this guy, drawing this guy, oh, it looks like this guy upside down and shifted up 4 units, right? So there's going to be a point of intersection that will be a circle, and you know, just to make it really clear, let me draw it a little bit bigger. So this keeps going up, right? I have to stop it somewhere, but it keeps going up. Okay, that's going to have to be dotted once I get the other one in there. Okay, and then this guy is at, the vertex is at a height of 4. It opens down, right? They intersect somewhere. It keeps opening down. But really, and then, yeah, okay, it'll look like that, I guess. And that's what a very rudimentary picture would look like. This point would be at 0, 0, 0. This point, where would this point be? And again, it's the one in pink is this guy, right? 0, 0, 4. And so the actual region created would be kind of an egg shape. So you'd have the top part given by z equals 4 minus x squared minus y squared. Terrible. Let me try that again. And then you'd have the bottom part given by z equals x squared plus y squared. And so the region we're integrating over is the interior of this thing. So that's Q. Does that make sense? All right, so we're going to go with the usual order of integration here. And what is the usual order? dz, dy, dx. So the integrand is 1 because we're trying to find the volume. dz, dy, dx. All right, so to find the inner limits of integration, just find the roof and the floor of Q. So the roof here, given by that function, and by the way, this is only going to work if you're given one function for the roof and one function for the floor. Otherwise, you'd have to break up the integrals, and hopefully you won't get something that ugly. So there's the roof. There's the function that gives the roof. And the bottom of this corresponds to the function that gives the floor. So these guys are our upper and lower limits of integration. And it's already solved for z. If they weren't solved for z, you'd have to solve them for z. And that's where you can run into trouble. Sometimes it's not easy to solve for a particular variable. Okay? This case, it's super easy. So the bottom guy is actually given by the bottom limits of inner limits of integration, x squared plus y squared. Upper, 4 minus x squared minus y squared. Now, the rest of it you get by projecting this weird-looking egg shape down in the xy plane, and that becomes your region of integration for the outer two, or corresponding to the outer two limits of integration. It's just like a double integral at that point. So if I project this thing down, let me move this. So think of the sun as being right above this thing. It's going to be, what's going to show up? It's going to be the widest value that shows up, right? So you project straight down, and that's going to be, the boundary of that is going to be a circle, isn't it? Right? And so, and there's the center of that circle at 0, 0, right? So the question is, what is that circle? What is that circle going to correspond to? Well, isn't it going to be, except for the z component, or z coordinate, isn't it going to be the same equation as this equator-looking thing? Yeah. So, well, the z value is the same at this point, right? So couldn't we just set the right-hand sides of these equations equal to find the xy equation of that curve of intersection? Which is going to, if we drop z down to 0, that's going to be what this curve is, right? So that's exactly what we're going to do. To find the region in the xy plane by projecting Q down into the xy plane, we're actually going to have to solve the equation that we get when we set the right-hand sides equal. So 4 minus x squared minus y squared equals x squared plus y squared. And what would be a good idea here? Probably combine like terms, right? So how about I'll move the x squared and y squared over here and turn it around, get what? 2x squared plus 2y squared equals 4, or x squared plus y squared equals 2. So that's this circle in the xy plane. Keep in mind this circle down here is in the xy plane. Okay. So you might think, oh, let's switch to polar, but it's probably a good exercise to set it up, at least in rectangular. So this is a circle of, what's the radius? 2, centered at 0, 0, so 1.4 something is your radius. That circle looks kind of like that anyway. It's hard to draw it freehand. And then if I set up the differential or dy dx, that means I need the top function and bottom function as the equations y in terms of x, right? So what would I get if I solve? I'd get two values if I solve this for y. One of them will be the bottom function, one of them will be the top. What will that be? Y equals plus or minus. Yep, exactly right. The plus root's the top one. The top function, which goes from axis to axis, right? Or from this point on the x-axis to this point on the x-axis. And then the bottom one is the one that remained in pink, which is the negative root. Is that pink or purple? Oh, you guys are as bad with colors as I am. That's why you're in Calc 3, right? You're not in fashion. Okay. All right. So what does that mean then? Well, set it up just like a type 1 region where you have vertical rectangles for a double integral. And the bottom and top of that rectangle will give you your bottom and lower limits of integration on the middle integral. So from negative 2 minus x squared to positive 2, square root, that is, 2 minus x squared. And then what does x range from? In this picture, x ranges from, well, the radius was square root of 2, right? So negative root 2 to positive root 2. And there's your setup. But you'd be a fool to evaluate it using those outer limits of integration, the outer two, for the middle and the outer limits of integration. Because hopefully it's clear you can use, at least after you get done with the inner limits of integration, you could use polar, right? Which would be way easier. But it was a good exercise to set it up. Okay, so let's go through the evaluation here. Okay, for this inner guy, we're going to evaluate with respect to z first. What's the integral of 1 with respect to z? Z. So we end up with, okay, the outer, okay. Instead of writing these limits of integration, I'm just going to put the set that we're integrating over, which is x squared plus y squared is, technically it's the interior of the circle. So it would be less than or equal to 2. X squared plus y squared is less than or equal to 2. Okay, that's like saying r over r. Okay, that's r. And then we integrated the inner one and got z, and we're going to evaluate that from what to what? Oh, x squared plus y squared to 4 minus x squared minus y squared. And then we still have the dy dx on the outside. Okay, so fill it in. We still have the x squared plus y squared less than or equal to 2. That's our r. So that's a double integral over r of, okay, plug this guy in for z, you get 4 minus x squared minus y squared, minus the entire thing here, minus x squared minus y squared, minus the quantity x squared plus y squared becomes minus x squared minus y squared dy dx. And so what does that become? Double integral of what? 4 minus 2x squared, right? Minus 2y squared. Everybody agree with that? Is that okay? Switch to polar. So if you want, you can go back up and look at that circle and switch to a representative sector to make your life a lot easier. You can just use a spoke if you want. Make a line from 0, 0 to the edge of the circle that covers your entire region that you're integrating over. And then what does R run from then? 0 to root 2. And this region is the entire disk. So what is theta going to run from? Think angularly from 0 radians all the way around to 2 pi radians. Okay. So when we set it up, the limits of integration in polar then, which is why I didn't bother to keep writing them in rectangular in case you were wondering. Remember, you have an extra factor, r, and then dr d theta. I'll do the 4, I'll convert the 4 minus 2x squared minus 2y squared in a second. R runs from 0 to root 2, right? And then theta from 0 to 2 pi. How can you rewrite this? 4 minus the 2 times the entire quantity, x squared plus y squared, right? Which is just r squared. So make sure you realize what I did there. The minus 2x squared minus 2y squared is minus 2 times x squared plus y squared quantity, which is just r squared. Okay? You get a reasonably easy integral to evaluate, so I'm just going to give you the answer. You guys can get more practice here. I'll put a dot, dot, dot. You should get 4 pi, pi. But yeah, these are ones you should practice integrating efficiently, right? Break up the integral into a product of integrals since you have constant limits of integration and just a function of r inside. Distribute the r, go to town. Okay?